Hello, welcome to this lesson in the AC Circuit Analysis Tutor. Here we're going to start a batch of lessons that deal exclusively with power calculations when you're talking about AC or sinusoidal analysis. All right, so a lot of the concepts that you've learned in elementary analysis with what is power, positive power, power absorbed, things like that, those simple equations, I squared R, those equations, a lot of them are going to have very similar kind of analogs in the AC domain. However, we can't just jump to the punchline. Believe me, I want to just be able to give you all the equations and write them all down and say, here are the AC power, equations, and then we'll just solve a bunch of problems. The problem with it is there's a lot of theory in where they come from. And believe me, I don't like covering lots of theory unless it's really important. But I'm going to go through these batch of lessons explaining every step of the way where these equations come from and why they're important. Because when you're talking about AC analysis, there's a lot of terms involved. Because suddenly it's not just power anymore. There's real power, and then there's reactive power, right? And then you can get positive power and negative power. We'll talk about that. You can talk about energy transfer between, backwards and forwards. We'll talk, about that a lot later on. And we'll be plotting power a lot. And that kind of stuff you just never do in DC analysis. So there's a lot of terms that you have to understand. Also, the units of power can look a little bit weird. We have watts, but then we have VARs and things like that. So we need to talk about these terms. We have leading power and lagging, power and power factor and things like that. So I'm getting ahead of myself, but I want to just caution you to stay with me. It's very tempting to skip ahead and say, well, just go ahead and give me the equations. But the problem is you're going to see some things that I'm talking about, and you won't understand what I'm talking about unless you follow me through it. So I'm going to take you in baby steps, maybe a little bit slower than some of you want, but I'm going to take baby steps, and we're going to work our way through it. And I promise you that if you do that, if you follow me through it, you will not only understand how power works in alternating current, but you'll be like, wow, that's really cool, that's really elegant. And you'll come back and refer to these lectures over and over and over again. All right, so let's start our journey together. We're going to do some review. We're going to talk about some stuff that we learned in the very beginning of circuit analysis, right? So if you can kind of pull your brain back to many, many moons ago when we talked about the basic idea of what is power. We had this concept here. I'll just draw a square here. And we said this is a load, right? So for now, you can think of it as being a resistor inside, but in reality, this load could be an inductor, a capacitor, or it could be a mixture of all three. It could be 25 inductors with 10 resistors. It could be anything going on inside of there. And that load is going to have some terminals that come out of that load. We don't really know what's inside the box. That's okay, but we know that there's some terminals here, and we have a voltage source on the outside that's sitting there, right? Now, in the DC case, it's just a constant voltage, but keep in mind that for AC, this voltage source, even though I have plus minus, it's really oscillating back and forth. This is just kind of the reference direction we're drawing. So if the voltage source reference direction is like that, then we're going to say the current is flowing in. But again, keep in mind the current really is going in and then out and then in and then out because it's an alternating current kind of situation. And these are both sinusoids. We'll write them down a little bit later. Now, if I want to write down the equation for the power absorbed by this load, right? Remember, we talked about that. We said the power, P, so I'll put a note here. Way back when we talked about the sign convention, we say that P is positive if the current I goes in the direction of a voltage drop, right? Which is exactly the way I have it drawn here. So you can see this voltage is here, so you can see plus minus would be right here. The current is going in the direction of a voltage drop, so we talk about power being absorbed by the load. We have power is equal to I times V. We'll write it down in a second, but current times voltage, and we keep a positive sign out in front because the current is going in the direction of a voltage drop. So in this case, we say that the power is absorbed by the load. And I know all this stuff is elementary. You just kind of have to hang out with me for a second. But then we have another case that we're going to talk about in a minute, and we talked about this briefly in the past. We said that the power is negative if the current I goes in the direction of a voltage rise. Now in this case, the voltage is plus minus, so the current's not going in the direction of a voltage rise, but if you think about it, when you have those voltage sources, You know, you have plus minus in the circle, the current comes out of the circle, the current's going in the direction of a voltage rise for all of those voltage sources that we have connected to all of these networks we've been talking about. So in those cases, if we were calculating the power of that source, we'd have a negative that we'd have to stick in front of the power calculation, and that corresponds to the case when power is delivered or supplied by, in this case, source. Now this was the convention that we used for power calculations a long time ago. We said P is equal to I times V. You put a positive sign in front of it if the current goes in the direction of voltage drop. You put a negative sign in front of it if the current is in the direction of voltage rise, like you would typically have for sources. All right? And what we're kind of dancing around here, because I've said it a few times verbally, but the power, little p, is equal to the voltage times the current. You know, there's a joke in circuit analysis or in electrical engineering that if you just know P is equal to IV or V is equal to IR or something like that, then you can solve any circuit. It's true, right? But there's a little details along the way that make things a little bit more complicated than that. Positive sign in the case of the current going like this here, negative sign gets put in here if the current's going in the direction of a voltage rise. But things get a little bit more complicated in terms of these kinds of problems, right? Because in AC circuits, the voltage is a sinusoid and the current is also a sinusoid. So in general, we have something like this. We say that the voltage is going to be equal to Vm, which is the magnitude, times the cosine of omega t plus some phase angle, theta V. Now this is a voltage, so we're going to say this is volts. That's the unit there, right? So this should not come as a surprise. This is kind of like the time domain representation. We usually talk about phasors, but I'm writing the time domain, magnitude, frequency, phase angle, and we're always talking about cosines in electrical engineering. The current is going to be very similar, except the magnitude, we're going to call it I sub m. That's the top of the curve times the cosine of omega t plus some phase angle. We're going to call it theta I because it's a different phase angle than this one. And that's a unit of current, so we call that amps. So again, magnitude, that's how high the curve goes. Frequency, this is the angular frequency, how many radians per second, how fast the oscillation is. And this is a phase angle. This means how far from zero is that cosine shifted, because we all know that cosines start out at the maximum, and then they go down and then up and then down and up. So if you have a phase angle here and here, it's telling you how much of a shift along the time axis, or the horizontal axis, back and forth this way, is this guy look. Now the current can have and usually does have a different phase angle than the voltage, and that's why we have the subscripts here. All right, so we need to have some kind of a reference though, because we have arbitrary phase here, voltage phase and a current phase. Now this is just kind of taken, you'll see it in your book, it's not something we're going to derive, it's just a convention, just like we have the sign convention here, we have a convention in power calculations, that we are going to use the convention that the current, whatever it is going to be a maximum at t is equal to 0, right? It's just a convention. We want to set it up that way. So we have to have a time that we start the clock at, right? That we start observing the circuit, right? And we're going to fiddle around with these phase angles so that when the clock strikes 0, when the stopwatch starts, the current is at its maximum. And it, because everything's going on forever and ever and ever. So you have to have some kind of time convention. What happens at t0? We want this current to be a maximum at t0. But if we put t0 in here, this will be 0, then we'll have cosine of some phase angle, and that's not going to be a maximum. What you really want is the entire inside of the parentheses to be 0, because cosine 0 is 1. We want the maximum current at t is equal to 0, but this phase angle that we have for current is arbitrary, and we don't know what it is because it's different from circuit to circuit, but it's screwing that guy up. So in order, and I'm going to move over to the next board here, in order to get that reference exactly the way we want it, we're going to have to subtract this phase angle from the inside of here. And this is just kind of background stuff. So we want as a reference, t is equal to 0, we want the current I to be a maximum, which is I sub m. We want the maximum point. We want the top of that curve to be there at t is equal to 0. So the only way to really do that is to shift it back by theta I. So we shift by theta I. And I'll show you what I'm talking about in a second. In other words, the new current that we're really going to be talking about is going to be I sub m times the cosine of omega t. Remember, it was plus theta I, but let's subtract off a theta I, right? So then you don't have any more phase angle in there. So basically what we're saying is we want this to be a maximum at t0, so we'll just subtract the phase angle theta I from here. But you can't just do that without any other ramifications. You can't just subtract the phase angle and just throw it in the toilet. You can't just do that because it's there. So what you really have to do is maintain parity between the relative difference in the phase angles between the voltage and the current. So the bottom line is if you're going to subtract a phase angle from here, you need to also subtract the same phase angle off of your voltage because you want to maintain, relatively speaking, between the current and voltage, you want to maintain a relative phase between them that's always the same. So if you're going to subtract a phase angle from here, you need to subtract it from here also. So what that means is that the voltage is going to look a little bit different too. It's going to look like Vm times the cosine of omega t plus theta V, but I need to subtract theta I from it. Make sure you understand this stuff. This is not something you'll really be asked on the test. This is just convention stuff. Actually, this is current. So this is amps, and this is now volts. Let me take just a second to talk about what we're doing here, okay? You have a circuit. You have a voltage source out in front. That voltage source is sinusoidal. It starts shooting, or not shooting voltage in. You know what voltage is a potential to move current around. But the voltage source is out there doing its thing. And then some current's going to flow out of it based on what's in the box, what's in the circuit, right? But the phase angle between current and voltage, the difference in phase between the current and the voltage, is governed by what's in the box. If it's resistors in the box, just resistors, then there's no phase difference. The current and the voltage go up and down as a cosine, and they're in lockstep. They both go up, they both go down, they both go up, they both go down, when the box is just resistors. Because resistors don't shift phases around between current and voltage. But if you have capacitors in the box, or inductors in the box, or a mixture of capacitors, inductors, and resistors in the box, then there will be a difference in phase between the current and voltage, because if you remember back to the definition, it all goes back to how capacitors were defined. You know, the voltage across an inductor, for instance, L times di dt, there's a derivative in there. So that derivative in the capacitor and in the inductor definition basically make it so that the voltage and the current, they're always going to be out of phase with each other. They're going to have a phase angle difference because of that derivative that's there. It means when when one component's changing rapidly, it puts the other one at a maximum. That's what a derivative does. So that's just a long story to say that whatever's in the box is going to govern the relative phase difference between current and voltage, right? So we start off with a general relation that says, hey, there's a phase angle here at voltage, there's a phase angle here with current, but we don't want this phase angle to be here just from a convention point of view. So we subtract theta I here, then we must also subtract it from here to maintain parity, lockstep between those two things. All right, I think that's enough talking about that. So this maintains the same relationship. These equations right here are exactly equivalent to these other ones. It's just a different way of writing it. So we take the phase angle here and we basically subtract it from both of them. All right, and now when t is equal to 0, we have cosine of 0, which is 1, which gives us I maximum. So at t0, the current is a maximum, which is what we want our convention to be. Now, if you go back and remember, power, any kind of power, instantaneous power, we're going to start calling it, is V times I. Now we know what V is, now we know what I is, right? So we're going to write that down. We're going to say that the power, little p, and the reason I keep saying little p is later on we're going to have capital P. So little p is instantaneous power, right? It's going to be the voltage times the current at any moment in time. So let's multiply these together. You'll have Vm times the amplitude here, Im, and then we have the cosines multiplied together. So we'll have the cosine of omega t plus theta v minus theta I, that's just this cosine, times this one here, times the cosine of omega t. All right, this is what we call instantaneous power. So I'll put a little, let me switch colors here a little bit, like this, and we'll call this little p, we'll call this instantaneous power. Instantaneous power. It's important that we say instantaneous power. We'll see as time goes on. And I'm going to write something down that's obvious. As time changes, the power at that moment also changes. So I know it kind of goes without saying because you know you're studying AC analysis, but you have to start thinking about things changing all the time. It's easy to think of current changing and voltage changing, but it's not a common concept to think of the power changing. But you really think about it, it makes total sense. The voltage is going up and coming down. The current is going up and coming down, and they're in general not lined up with each other. They're only lined up if whatever's in the box in your circuit is purely resistive. Other than that, the current and voltage are shifted with respect to one another. So sometimes the current will be positive, the power, sometimes the power will be positive, sometimes it will be negative, and we were going to study that in great detail. So it's very possible, in fact you'll see it all the time, that this power that we're talking about, this instantaneous power, depending on what's in the box, it could be negative. And we'll talk about what that means here in just a second. We're going to take our baby steps to get there. This is the full-blown glory of it. You have a cosine times a cosine, but keep in mind that these are shifted with respect to one another because of this phase angle here. Whatever the phase angle here is, the difference in theta v and theta I is going to cause these cosines to be shifted with respect to one another. So when we multiply them together like we're doing here, you can get some weird things. Sometimes positive power, sometimes negative power. All right? So this is what we call instantaneous power. As time marches on, the power changes because you've got these cosines multiplied together. So let's move to the other board, and we'll take the simplest case. We're going to take the next several lectures to talk about capacitors and inductors, and we're going to take this basic equation, we're going to blow it out with some trig identities, and we're going to study it in great detail. This is just the very first step along this journey. But we have enough on the board now to study, in theory, what's going to happen if you have a resistor in that box or some network of resistors. Resistors are easy, right? Because, well, what do we talk about? Resistors don't alter the phase angle between current and voltage. If you have resistors in the box, if the voltage goes up, then the current's going up in lockstep with it in terms of a cosine. They both track each other up and down if you have resistors only in the box. So let's look at that case and see what we can learn from it. If the load that we're talking about here is purely resistive, all right, then we know that I and V are in phase. That means they're lined up as they track up and down through their cosine cycle. And what does it mean in terms of math that things are in phase? It means that the phase angle of theta V minus the phase angle of theta I has to be what? If they're in phase, the difference in phase angles has to be 0. That's what it means in terms of electrical engineering when things are in phase. Whatever the phase of V is minus whatever the phase of I is, it's 0. That means they track each other perfectly. That only happens if the load is purely resistive. Okay, so there's no relative phase shift between current and voltage. So let's go and plot a few things that can make sense. So we say if resistive load, then let's draw a few things. I like drawing things occasionally, not all the time, but occasionally. So here's a plot, here's time, and we're going to draw the current. So that's the current we're going to draw. All right, let's go back and look at our current equation. We said that we wanted this to be we subtracted off the phase angle here, so this is now our new equation for the current. It's just simply a magnitude times a cosine. So we know that cosines start out at a positive value, right? They start out up here at a maximum, right? And then we're going to draw it like this. So this goes down, bottoms out, goes up, back to the maximum, and goes on and on and on forever. So that is what the current is going to do, and I'm going to draw some dotted lines because these can be very helpful. So I'm going to draw a dotted line coming down like this, all the way to the bottom of the board, and I'm going to draw one here, just to help me line some things up, and I'm going to draw one here. Forgive the freehand nature of this, but I promise it'll be worth it in the end. All right, so let's draw the next guy. If this is the current, what does the voltage look like in this case of a resistive load? Well, here we're going to draw time, and we're going to draw voltage. right? So we just said that if the load is purely resistive, the phase angle here is 0. The phase difference between theta V and theta I is 0. So that means if this is the formula for the voltage, this is now 0 since we were saying the difference in phase angle between current and voltage is 0 for resistors. So really you have Vm times the cosine of omega t. That's it. This is gone. So again, it starts at a maximum. So in the case when you have a purely resistive thing going on, this guy here, this was I sub m, this is the maximum current. Here we're going to have the maximum voltage amplitude here, and the guy is going to look exactly the same. Now I'm going to do my best to draw, probably going to screw it up, but it goes down here to 0, back up, back down, and so on. This should look exactly like this because, as I've been saying over and over again, when you have resistors, voltage and current track each other. Now, the amplitudes are different, of course. I'm drawing them the same, but the current could be, 1,000,000 amps, and the voltage could be, 25 million volts or something. They could be different heights, but the phase angles track up and down. Everything tracks. They're not shifted with respect to one another. So in the case of a resistive arrangement like this, this is what the relative current and voltages look like. So what's going to happen when we look at the actual power? So we're going to draw a third one of these guys. The instantaneous power, by the way. So we'll say P, instantaneous, little p, is equal to I times V. So we're going to basically need to multiply these two equations together. It's a little difficult to know what a cosine times a cosine looks like, but then you can look at these two cosines and you can say, well, this is a maximum times this will be a maximum. So then down here, this probably is going to be a maximum somewhere. So I'm going to draw that in kind of start my little curve up here. I know it's going to start here, but then we get down here to the point where both of them are declining, so we're going to decline. Eventually, they're both going to get to 0. 0 times 0 is also going to give me 0, so we know the curve is going to get down here. But then notice, so let me go ahead and start drawing. Go down here. But then what's going to happen down here? On the other side, this is a negative I, negative, times a negative V. Negative times negative gives you positive from algebra, right? So this does not dip below the axis. This goes back up. And I'll just kind of continue it on here like this. That's not perfect drawing. It goes down here, and it goes down here. Okay, so that's not a perfect drawing, but you get the idea. What's happening here when you multiply these guys here, anytime they're positive, but anytime they're negative, since they're multiplied together, they're also positive. So when you have this power here for resistive load, you do get this oscillating thing going on for instantaneous power, but it's always positive. Even if the current turns negative, the voltage also turns negative, and since negative times negative is positive, you still declare yourself to having positive power. Notice this is a negative maximum corresponding to another maximum power here. This is a positive maximum in current and voltage, giving you another positive here. So you have kind of a doubling of the frequency of the power here, but it's always positive. It never ever dips negative. And that's actually really important. Why? Because a resistor is just a resistor. It's just literally a thing in the box that just literally can dissipate power. That's all that it can do. Resistors can just dissipate power. That means that power, instantaneous power, is always going to be positive for resistors. Resistors can never store energy. There's no mechanism to store energy. Literally, electrons go through, vibrate the material, and heat is given off. So power is always lost in a resistor. That's why when you take, in the case of a resistive load, when the current and voltage are lined up, you multiply everything out. Even in the AC case, you see the power going up and down. Of course, the power is a maximum here because the current and voltage is maximum. The power is a minimum here because both current and voltage are crossing into a minimum, so there's less power being dissipated here. But then it climbs back up, and then it goes to 0, and it climbs back up again in accordance with this. But no matter what, no matter how you slice it, a resistor can never, ever, ever store energy. So it can never, be stored for later release, right? Now I'll just kind of give you a little bit of a preview from the point of view of this guy. We just did it for resistors, right? To just show you that, hey, power really can oscillate depending on what's going on here, but in this case, it's always positive. If you have inductors or capacitors in that box, then this instantaneous power is going to dip negative, right? It's going to actually be negative power during certain parts of the cycle. And for inductors, it'll actually be negative power for certain parts of the cycle. And I don't want to get in too much into it now, but the basic reason why you can have negative power for inductors and capacitors is because inductors and capacitors can store energy. That's the difference between resistors, right, and inductors and capacitors. You say, well, how can that happen? Capacitors can temporarily store energy in the electric field between the plates. And then later on down the road, that energy can be pulled out of the capacitor, right? In the inductor case, energy can be temporarily stored in the magnetic field that's in the coil, stored in the magnetic field that can then be pulled out later. When I say later, I don't mean like a battery, like store it for 10 years. I'm saying later in the cycle, as everything oscillates, then the power can be extracted. So for inductors and capacitors, you have this give and take where you can give some energy to the inductor, where it's absorbing power, and then it can kind of give back to the circuit later. And then you can have this give and take. We call it sloshing. Energy can slosh back and forth when you have inductors and capacitors stored in the magnetic fields and the electric fields there. But that can never happen for a resistor. So the power always stays positive. It stays on top of here, and it never ever dips negative. So I want to make sure I covered everything. We basically say here, I think I pretty much made it clear, but here, P is equal to IV, but I'll just write it down. What we're really plotting here is Vm Im cosine omega t times cosine omega t. And this one is just from the current, but the voltage is 0 as well because the phase difference here. When we go back here, we just said this was equal to 0 because they track each other when you have a resistive load. So that's what we're plotting. I'm going to make sure I have everything there. P is always positive, power is always absorbed, and things will look different if we have inductors and capacitors. That's about all I want to say for this lesson. We haven't done any circuits yet. We haven't done any problems yet. We have to cover this groundwork. If I just skipped it all and said, here's the equation for power, then you'd be like, what? So let's just quickly review. Basically, not too much has been done. We have a load. We know P is equal to VI. It's always true, whether it's sinusoidal, steady state, or not. Here are the equations for the time domain versions of current and voltage. And then we said, hey, we have a convention. We want the current to be a maximum when time is 0. So we shift both current and voltage, shifting off by theta I. This makes 0 here, and then we have this ugly looking term there. We multiply them together to get the instantaneous power, which means as time changes, the power at that moment also changes. And then we just drew a picture of one case. We have a resistive load. Here's what the current would look like. The voltage is going to track it in phase when you have a resistive load. And then you can easily visually multiply these together, and you can see that it looks like this, always staying positive, but always changing. And that is what you need to kind of get in your head. Power changes in AC. It's never the same. It's always moving up and down. But resistors are nice to look at because we can talk about it and you can understand it. Now move on to me with the next section. We're going to study some more terms. Eventually we're going to get into what is reactive power, which is the power associated with the inductors and the capacitors, and we'll put it all together. We're going to take several lessons to get there, but you'll have a really good understanding of it. So follow me on to the next section and we'll tackle it step by step as we move forward.